Good evening and welcome to this Institute lecture. I'm Robert Dijkgraaf, Director and Leon Levy Professor at the Institute for Advanced Study. And today is special because I'm not only welcoming members and faculty and friends of the Institute, but also the trustees, because this public lecture is part of our trustee meeting. And we'll be hearing actually about the latest news from the cosmos from one of the best persons to interpret it, Matias Zaldarriaga, professor in the School of Natural Science at the Institute. And as you know, we have quite, Matias is from Argentina, and in fact we have quite a representative here in Argentina because Juan Maldacena is studying the small particles just as Matias is studying the universe as a whole. And I think Argentina is doing quite well in general because this year we just came back from the coronation. They now have a queen, the Queen of the Netherlands. They have a pope. They have the best soccer player. And then they have the two experts, the best experts in the universe and the small particles. So between that, I think you have covered a lot of grounds. Matias has studied the universe and so is cosmologist as well as astrophysics as a tool of studying new physics. And he has many influential contributions. But particularly, he developed a technique for calculating the cosmic microwave background that we heard about, the kind of the baby photo of the universe, and calculating this with numerical programs, and that actually became very famous for that. His recent research has focused on intergalactic hydrogen gas in that early universe. As I told you, he's from Argentina, studied at the University of Buenos Aires, and then at Massachusetts Institute of Technology, earning his PhD in 1998. Matias is very familiar with the Institute. He has been a long-term member here from 1998 to 2001, and then he was a Keck visiting associate in cosmology from 2001 to 2002. He served on the faculties of New York University and Harvard University, where he became full professor in 2004. And his appointments were both in the Department of Astronomy and in Physics. In 2009, he became a professor here at the Institute. He had many honors, and just mention a few: the Gribov Medal of the European Physical Society in 2005, the Warner Prize by the American Astronomical Society in 2003, a MacArthur Fellowship, as well as fellowships from Packard, Sloan, and Hubble. All these honors and many others have recognized his groundbreaking work on the interface of cosmology and particle physics, as well as his unique ability to understand the clues of the very earliest moments of the universe. So I'm very excited that we'll hear from him the latest finding of the Planck Satellite and what they mean for cosmology. I want to close with a little anecdote because you see this beautiful picture here. But there was an earlier version of that I actually quite often showed to my children, and there you could actually recognize the symbols SH, and often it's said it was Stephen Hawking's signature. And, but then this new picture came about. It was on the front page of the New York Times, and I showed it to my children and said, hey, the signature went away. But I said, if you close your eyes, you see again the thing in low resolution, and then the signature is back there. So that's, I think it's a metaphor often, as in journalism say that too much research can destroy a beautiful story. So that story is gone, but I think there's many new stories that we'll hear. At the end of the lecture, we'll have, as always, a question and answer period. And please welcome me now. Join me in welcoming Matias Zaldarriaga to the stage.
Thanks very much, Robert, for that kind introduction. I'm sure it's not as exciting to introduce me as it is to introduce the King of the Netherlands, but I was hoping you would be wearing the same nice outfit we saw in the pictures. Maybe for this evening. Okay, so I want to tell you about the results from the Planck Satellite and about cosmology, the state of the field these days. In the 1930s, we discovered that the universe was expanding, and since then, there's been great advances in our understanding of the universe, what it's made of, how it has evolved through cosmic history, mainly through the interplay between beautiful observations made with ever better telescopes and ever better cameras, and also our ability to model this, what we see with the telescopes. And on March 21st this year, we got next installment from our experimentalist friends of new data about the very early universe, a picture from regions of the universe when they were only 380,000 years after the Big Bang. The current age of the universe is 14 billion years, so this is a picture of the very, very early universe that I'm showing here. It was produced by the Planck Satellite, and it kind of gives us the initial conditions for the process of formation of structure in our universe. What the Planck Satellite actually did is produce 9 maps of the sky. This is a full map of the sky. The ones of you that got here early, you saw this little movie of what this actually represents. This is the same projection of the Earth. In the same type of projection, the surface of the entire Earth would look like this, and this is a projection of the map of the full sky. What the Planck Satellite did is it made 9 maps of the sky in 9 different frequencies. Those maps contain not just this early light from the cosmic microwave background, but light produced by many other processes, including electrons going around the magnetic fields in our galaxy, light from little dust grains in our galaxy, light from little dust grains in faraway galaxies. It also has in it a map. If you dig in the data, you will find a map of the hot gas in the universe through the Sunyaev-Seldovich effect. You will also find a map of the dark matter in our universe through the gravitational lensing effect. So there's a lot of stuff hidden in that data. We've learned a lot from it, and of course in this lecture it would be impossible for me to go over all of that. So what I've done, or what I'll try to do, is walk you through some of the things that are closer to my own interest, so that and give you a sense of perspective of where the things that we have found fit in place. In order to do this, what I will start doing is give you a brief lining review of modern cosmology, and I'll try to do this as fast as possible in order to get to the latest results from Planck. So if you measure the properties of the universe 14 billion years ago, you will find a universe that's very different from what it is today. The universe today is expanding, as I said, but it's expanding rather slowly. It takes 14 billion years for the universe to expand appreciably, say to double in size. If you went back to the beginning 14 billion years ago, it would be doubling in time incredibly fast. In a small fraction of a second, the universe would be twice as big and twice as big and twice as big, really, really fast. Today, if you think about the universe, you would say the universe is very cold, and if you associated a temperature with to it, perhaps you would associate the temperature of this cosmic microwave background that I will be talking about. It's 3 degrees Kelvin, 3 degrees above the absolute zero. If you go back 14 billion years ago, the universe was so hot and so dense that filled with particles, filled with things that were interacting with one another. It was so hot that the energies in the collisions of these particles were probably much higher than any energy that we have been able to explore in the laboratory here on Earth, including those that we produced at our latest machine, the Large Hadron Collider in Switzerland. The universe, as I said, it was filled with stuff, while today, if you think about the universe intergalactic space, you would think of an empty space and vacuum. It was not like this. It was teeming with particles. It was a very different place. As time goes by, this expansion slows down, the universe cools down, things start to form. Eventually, the first things that form around a minute after the Big Bang are nuclei, so the light elements like helium and deuterium form in this first minute. We can go out with our telescopes and measure the abundance of these objects, of these nuclei in very old stars and pristine blobs of gas, and we can compare what the abundances of these things that are supposed to be produced a minute after the Big Bang with what we see in our observations, and there's agreement. So we think we understand what was happening just a minute after the Big Bang. If you wait a little bit longer, the next thing to form are atoms, hydrogen atoms, and that's the time from where we get this picture of the universe 380,000 years after the Big Bang from the cosmic microwave background, an actual picture of regions of the universe at this early time. You keep waiting a little bit, and eventually a billion years passes, and bigger things start to form. Eventually galaxies form, stars form. We see those galaxies with our telescopes. We map where they are. And as a result, we have a detailed measurements of what the universe was doing as a function of cosmic history with pictures, real pictures that we can take with our telescopes. So I'm sure some of you are wondering, how is it possible that we have pictures of the past? Okay, so let's not lose people so early in the talk, and let's just explain this in fact. So the point is the following. Light takes time to go from one place to another. So if with a very good telescope you manage to get a picture of something that's very, very far away, light had to start traveling a long, long time ago to get to us. So you're seeing how this thing was in the past. And as you get a better telescope and look at something further and further away, you take pictures of things as they were in the past, further and further back in the past. So when I tell you that we have these pictures from these various moments, this is because we've been able to build bigger and bigger telescopes, better and better cameras to see things that are further and further away and thus are fainter and fainter and fainter, but you can still find them. So they're real pictures. It's not, it's a history made out of real pictures that we can take. Now, if we want to understand what these pictures are showing us, if you want to build a model for it, especially if you're interested in what's happening after the first tiny fraction of a second, we have developed by now a pretty good model. What goes into this model? The first thing that goes into these models are the laws of physics, as we have already tested them in the lab on Earth. And for astronomy and cosmology, perhaps the most important law of physics that we need is to understand how gravity works, and that is given by the law of general relativity as postulated by or discovered by Einstein. Okay? We need to understand how these particles interact, so we need the laws of quantum mechanics, we need the standard model of particle physics, but basically we just need the laws of physics as we know them in the lab. And even though we are using it to understand things that happened 14 billion years ago, or only 380,000 years after the Big Bang, it appears that the same laws apply just fine. Okay? Even though these places are very far away, both in time and in space. We don't see any evidence, or it looks like we can live with the laws of physics that we already know and love. And the next thing that you need is you need to know what the universe is made of. And we think we have determined this pretty well. This is the result of what the universe is made of after these measurements by Planck. So if you imagine taking a very big region of the universe and seeing how much of various things there are. Ordinary matter, the stuff that you probably would be familiar with, regular atoms, light, and so on, apparently comprises just 5% of the total amount of stuff. Roughly like 27% of the total is dark matter. What is dark matter? Dark matter is supposed to be a particle that was left over from the very early on in the Big Bang, and it's around us, and there's a lot of it around us. And unfortunately, we haven't been able to produce this particle in the laboratory in any of these experiments, including the Large Hadron Collider, and we have not been able to catch it as it passes through the Earth. We think it passes through the Earth all the time. We've built detectors on mines to try to see the influence of this wind of dark matter particles as the Earth travels around the galaxy. We haven't been able to see that, but the universe is filled with a lot of it. And furthermore, around 70% of the rest is what we these days call dark energy, or the cosmological constant, or the vacuum energy, which is what we believe is the energy density of just empty space. So even if you have completely empty space, it has certain energy density that produces gravity. And most of what the universe is made of today, at least, is this dark energy. This is what we think. Now, I'm sure you're thinking, oh, he began by saying everything is fine, and we now understand everything, but he goes to a rundown of what it is the universe is made of, and it appears he's making everything up, okay? And it's indeed true, and this is what you should be thinking. However, we are pretty sure that this is the case. Now, let me tell you why we're pretty sure that this is the case. Of course, what's the first thing to think if you start seeing this? You say, okay, how is it that we know about the abundances of these things? It's because we infer them using the law mainly of gravity. So probably the first thing to think about is this is not there and the laws of physics are wrong. Okay, we've tried many decades trying to do it. And as we tried and tried, I would say that we have not yet found any convincing, even self-consistent modification of the law of gravity that even makes sense very much by itself. And trying to make these more or less toy models of modification of gravity that we have maybe have been able to write at some level, agree with observed facts, impossible. So far has been impossible. And in the meantime, as these 30 years or 40 years or whatever has passed, there's been more detailed and detailed observations of various things in the universe. And this simple idea that the universe is filled with dark matter, which is very predictive, you can calculate everything, has been working. So this is why we're getting very certain that this is indeed the case. One thing that I need to say is that all of this is really some picture version for detailed equations. We go do calculations and compare what we see. So it's not just words, it's detailed calculations, okay? So, and the other thing that we've tried to do is said maybe, okay, we're inventing this dark matter and dark energy, maybe we can make more complicated versions of it. Maybe this thing evolves with time, maybe the dark matter interacts with us in ways that are not the gravity. We've tried complicating this picture and we have found no evidence for it. We're trying to find evidence, we're trying to break this. It's not that it's the thing that we love the most, but it seems to work. Just to get to Planck, I need one final detour, which is to talk about structure formation in our universe. So the stars that you might see in the night sky with your eyes are just the tip of the iceberg. There are hundreds of billions of stars in our own Milky Way galaxy, okay? And our galaxy is nothing particularly special. There are hundreds of billions of galaxies in our universe, probably. And there are galaxies that are bigger than the Milky Way, galaxies that are smaller than the Milky Way. So there's all kinds of galaxies, ones that look like nice spiral galaxies. Now it looks like blobs of stars. These galaxies furthermore organize themselves into even bigger structures. Sometimes they form clusters or groups of galaxies in which these galaxies are moving up at around 1,000 kilometers per second around what we think is big concentrations of dark matter. A big concentration of dark matter and the galaxy is moving around 1,000 kilometers or 1,000 kilometers per second. Okay, so there's even bigger structures than that we call the large-scale structure of the universe. On the left here is a map of the position of nearby galaxies. Each dot here represents an actual galaxy as measured, its position measured by the Sloan Digital Sky Survey. And you can see, especially if you start zooming in a better picture, and you can even fly through the whole thing, you can see all of these big structures, we call them walls, regions where they're more empty, we call them voids. Notice that in this picture, each of these galaxies is just a point. So these are structures much, much bigger than galaxies. Galaxies from this point of view are just points. And the universe managed to produce this incredibly large-scale structure. Or what we call the large-scale structure of the universe. How did this come about? In our model, we can tell you exactly how it comes about. It comes about through what we call gravitational instability. What is this? Imagine you start the universe with a little small differences in density from one place to the next, okay? So there's a little bit more stuff here. The force of gravity towards this point is slightly stronger, so stuff starts accumulating in this place. And as time goes by, then the force of gravity is even stronger to there, and things start accumulating, wait billions of years, and you start forming things. That's what we think happens. We can calculate this process using our models. And one thing that I want to stress is that in all these calculations, to make this model agree with what we observe, with all these beautiful maps that we have observed, the dark matter is not some small modification that around the corner makes things look a little bit better. It's just the whole thing. It's the most important thing there. Most of the stuff that clusters is the dark matter. So really, the regular matter is following what the dark matter is doing. So if we didn't put dark matter into our model, it would be a disaster. Okay? And what is the importance of these pictures of the cosmic microwave background? These pictures of the cosmic microwave background are pictures of regions of the universe so far into the past, before this process of accumulation of matter could have had much time to happen. So we are seeing how the universe was before all of this structure had time to develop. So we are seeing the initial conditions for this process of structure formation. Then with the telescopes, we take pictures later and later on, and we try to see if our model can reproduce all the objects that we see as forming through cosmic history, starting with these initial conditions that we can now measure very, very precisely. Okay? That's the importance of the cosmic microwave background. So the cosmic microwave background is this light left over from the very early universe. It was first discovered by Penzias and Wilson almost 50 years ago. Penzias and Wilson were working in Bell Labs here in New Jersey. They discovered this cosmic microwave background. This was one of the original strong evidence for this model of the hot Big Bang, which I'm describing to you. What happened next is through time, people realized that this process of structure formation, it meant that if we take this picture in detail of the cosmic microwave background, we should be seeing these initial conditions. So there was a big effort to try to make better and better maps. Well, first to find these differences in because we're taking a picture so early in this process of structure formation, the differences that were there that led to structure are very, very small. Only difference in 10 parts per million. So even getting to them, finding them in this map of the cosmic microwave background was very, very challenging. it was this anisotropy was first discovered by the COBE satellite in the 90s, okay? And what has happened since then is something that you might be familiar with from your digital photography, from your camera. So what happens with the cameras? They get better, they have better and better, they call them the number of pixels, 10 megapixels, 5 megapixels, more and more megapixels in order for you to buy a new one. And what those pixels are those little squares that you see if you zoom in into the picture, that's the resolution. Okay, so if you want to get a good picture, you want a lot of megapixels. Okay? This first map of the entire sky made by the COBE satellite had only basically 100 pixels. It was a 100-pixel camera. So this progression was a progression in getting better, more and more pixels to this camera, and also the detector on the back of your digital camera also is getting better and better, okay? And so if you look at this progression, the first satellite from NASA was COBE, next one was called WMAP, the Wilkinson Microwave Anisotropy Probe. The W, Wilkinson stands for Dave Wilkinson, who was a professor here at the physics department. So WMAP had 10,000 more pixels than COBE. So the next over had 10,000 more pixels. And the detector, the camera, was roughly 50 times better. Okay? And Planck is the one that came after WMAP. I'm showing you pictures of it today. It had 10 times more pixels than WMAP and a camera which was 10 times more sensitive. And you can kind of see this in this picture. You can see this is the map as measured by WMAP. This is the map as measured by Planck. And if you take a small region, you can see that the structures that you can see in WMAP are much coarser because they had much fewer pixels in their camera, so they couldn't see the details that Planck can see. Okay? So Planck has enabled us to make a picture of the very, very early universe with much better angular resolution and sensitivity than the one we had before. Okay, that's what we've just received a few weeks ago. Nice, beautiful picture of the baby universe. Okay, great. So the next transparency is the one, or transparency. This shows how old I am. It's not transparency. It's a slide. Sorry. The next slide is the one slide that will have a curve and points and numbers, okay? But I need to show something like this. I'm sorry, because the data is so nice, so at least one thing with figure I need to show you. One figure with points and data and stuff like this I need to show you. So first thing to ask the question, what do you do with those maps? What do people do with those maps? So the first question that people asked was, how different was the temperature as you compare different regions of the sky? You first start by looking at big pixels, like the ones that COBE measured, big pixels, and say, how different is the temperature as I look at this pixel, this other big pixel, this other big pixel? And then I ask the same question with smaller and smaller pixels. So the pixels that WMAP measured, how different are they? The pixels that Planck measured, how different are they? And so on this scale, the x-axis is basically the size of these pixels. Here are small pixels, here are large pixels, okay? On the y-axis, what is shown is how different, a measure of how different the temperatures of, when you compare these pictures, how different they are. And the WMAP satellite was able to measure things around this region because it only had big pixels. The Planck was able to measure things for the smaller pixels that in this curve sit over here. The reason I wanted to show you this curve is for several reasons. First of all, I wanted to show you these points are the actual measurements, okay, with their error bars, okay? So this is incredibly precise measurements of this quantity. It doesn't matter exactly what it is, but it's been measured very, very well. And the next thing is that you see a line through those points. That line is our calculation based on this simple physical model. Okay, so this is what we predict. We should see 380,000 years after the Big Bang. The points are the actual measurements. It goes through it beautifully. It's incredible. Okay. In fact, what we have to do to see any difference is just take the points, subtract them from the curve, zoom in, and this is this is just try to see some difference, and then when you zoom in a lot, then you expand the axis a lot, then you start seeing some difference, and that's what we do. We obsess about these differences. Is this real? Is this the experiment wrong? Is the theory wrong? What's the problem? Okay, this is the state of cosmology, but notice how well we are able to match this, okay? And it's important to understand a few more things about this match. If you, what is going into this model? Of all these parameters that I told you about, or some of them I mentioned, to understand the physics of what was happening at this time, 380,000 years after the Big Bang, which leads to this nice curve with a lot of peaks and so on. All that you care about really is how much dark matter there is and how much regular matter is compared to the CMB, to this radiation in the CMB. Those are the two parameters that control all of this height. So we're fitting this with basically these two parameters. The physics is just from those two parameters. And the physics itself, the physical processes that are dictating the shape of this curve are very well understood things. They are general relativity, as I said. Then the interactions of this cosmic microwave background with the electrons mainly. This interaction is called Thomson scattering, after J.J. Thomson, which was an UK physicist, which was born in 1846, okay? So it's old stuff. The physics that goes into this is, we know it, we think we understand it. You need to know how the physics of the hydrogen atoms. What's happening here is the formation of hydrogen atoms. This is, we've understand from the beginning of quantum mechanics, maybe, many decades ago. So the physics that go into calculating this curve is very well understood. And we make the calculation and that's why we're getting so confident. We understand the physics very well. It just depends on a couple of parameters, and the measurements are beautiful, and the curve goes through the measurements, okay? So this is the reason we are so confident that we understand what's going on. For comparison, I'm also showing the kind of the state of the art of this around the year 2000. At that time, I was playing around a lot with, calculating these curves. At the time, we knew less about the model. The data had these big error bars, and we barely saw this peak structure. So, the field has advanced a lot, but the agreement now between the data and the theory is just incredible. And the other thing that I wanted to mention is that in this curve, even though you cannot see dark matter in this curve just with your eyes, believe me that if dark matter was not there, this curve would look completely different. Dark matter is setting how fast the universe is expanding at that time. Dark matter is already forming structures which is affecting the shape of this curve. The process of structure formation is already going. So dark matter is crucial. The curve would be completely wrong if dark matter was not there. This is part of the Planck story, but Planck and the other CMB experiments, but Planck also did a few other things that are very, very interesting, and let me show you some of them. One of the things that Planck was able to do, and it's very close to my heart, is study the effect of gravitational lensing on the cosmic microwave background. What is that? So, as light travels across the universe, if there is a concentration of mass, light gets bent. In fact, one of the first tests for general relativity was the calculation of how the light from distant stars would be bent by the sun. And thus, people went and tried to measure this shift of the stars during a solar eclipse, during an eclipse. And that's how GR was one of the early measurements of test of general relativity. What Planck was able to do now is look at the cosmic microwave background and figure out that as the radiation of the cosmic microwave background is traveling from these 380,000 years after the Big Bang all the way to us, and these dark matter structures are forming, they affect the cosmic microwave background and starts bending them. And as a result, the map of the cosmic microwave background that you see there is like it's been perturbed. Somebody has touched it. They could figure out that what we see is not what was actually there because the radiation was bent by this gravitational lensing effect. Okay? The effect is very, very, very small. Here is a little bit of an animation of how the map looks if the lensing was not there or if the lensing effect is there. The lensing effect is there in the universe. The difference is very small, and it's a great testament to how good this experiment is that they managed to pull this out. And not only they managed to see that this was happening, this depends on what? This depends on the distribution of dark matter all the way from where we are, say here, we're in somewhere over here, all the way how all the structure has been forming. It depends on all the distribution of dark matter all the way to the place where the radiation started traveling. And thus they can make a map of how this dark matter, which we cannot see with our eyes, we can now know where it is. This is the first map of the full sky of the distribution of dark matter in our entire universe, made by Planck through the effect of the gravitational lensing. So now we are, even though the dark matter does not produce any light, through this effect of gravitational lensing, we are able to see all the dark matter piled up in the different regions as the CMB travels all the way to us. And they did something also very nice that was something that probably, I believe it was not even thought of at the time Planck was being designed, which was, as I told you, these different the different maps of Planck contain a lot of information of many things. In particular, they have light emitted by little dust grains. What are these dust grains? Well, astronomers call these dust grains are little small particles, maybe having a few molecules or maybe a fraction of a micron in size. They are made of what astronomers call metals, which is anything other than hydrogen and helium is a metal. So and these are probably made of carbon, or they are, we know what they are made of, carbon, silicon, so different elements like this. The galaxies are filled with this dust. If you think of a galaxy, you're probably thinking of, you think of stars that emit light that you can see with your own eyes, optical light. However, this light, roughly half of it is absorbed by these little dust grains. As a result of that, these dust grains get a little bit hot. They maybe have a temperature of 20 degrees Kelvin, something like that, and they glow. They emit light that Planck was able to see. And thus, Planck was able to see this dust emission from distant galaxies that happen to be located in the same region of the universe that was bending the light of this gravitational lens, through this gravitational lensing effect, that was bending the CMB light, okay? In these dark matter regions that were supposed to be forming and that we calculated, and galaxies formed, and this little dust grain inside those galaxies emitted some light. And Planck was able to catch that light and through some fancy procedure isolate the emission of radiation from that dust. And what did they do? They pick out all the different lines of sight in the one of the cool things that they did is they pick out all the regions across the sky where they saw, say, for example, more radiation of this dust radiation coming in these different directions. They cut out little pieces and they put them one on top of the others. Those are the regions of the universe from which more of this dust, light created by dust is coming. Presumably this means there's more dust. Presumably this means there's more dark matter. Okay, and presumably this means that those are the regions in which you were to see the gravitational effect, lensing effect towards those regions, the photons will be deflected inwards. Then they took all the regions from which they saw less light of this dust light, and they also stacked them together. Okay, put them one on top of the other. And the final thing they did, they took this map of how the CMB was deflected that they made by analyzing how this picture was changed, and they put that on top of those maps. And this is what they got. And it's important to figure out that this is not a simulation. This is the real data. It's incredible for me that worked on this gravitational lensing a long time ago, that this is actual data. This is not a simulation. And it doesn't seem to be any error bars or anything. It's just beautifully the signal to noise is incredible. So what's plotted in the back is the amount of light produced by this dust. And so you see a lot of emission is red, a less emission is blue, and then on the little arrows show the reconstruction of how the CMB was deflected, and you can see that around these regions it was deflected inwards, around these regions was deflected outwards, just as is expected. Okay? So this means that we have a model that not only allows us to understand, how structure forms, it also allowed us to understand what was happening 380,000 years after the Big Bang. It also allowed us to understand how structure was forming across cosmic time, how it deflected the cosmic microwave background. The important thing, I'm not sure I already said, when we compare these maps and the sizes of these effects with what is computed with the model, works out, okay? And as I said, it's very important for this that dark matter is there. If you don't put it, it doesn't work out at all. In fact, with the cosmic microwave background, with these experiments, we are able to see regions at 380,000 years after the Big Bang that contain as much mass as clusters of galaxies that form later on. So we know exactly the initial conditions on the mass scales that we can observe them today. And there's nowhere enough time to form the structure that we see if we don't put the dark matter in the model. Okay? So this was another huge success, and making this measurement is very complicated. It's a very subtle measurement, involves comparing at least 4 points in the maps all at the same time, and it's a great advance in the field that we have now been able not to make this kind of maps. And a lot of other experiments, including telescopes in the South Pole and the Atacama Cosmology Telescope, they're all trying now to play this game and trying to reconstruct better and better maps of how all the dark matter distributed across the universe. And another thing that I wanted to mention is this map of the hot gas. They were able to see the presence or map out where the hot gas in the universe is. What is happening? As structures form, the gravitational potential energy in the formation is converted into heat, and some of the regular matter, the gas is being heated up, especially, for example, in clusters of galaxies. They get really hot. And they are so hot that when the CMB crosses through them, it takes away a little bit of the energy. And then the CMB that has gone through one of these regions with hot gas is slightly perturbed, and they can see this. This effect is called the Sunyaev-Seldovich effect, and they used it to map out where the hot gas is. As I said, a lot of this hot gas is in clusters of galaxies, so they used it to find new clusters of galaxies that had never been found before. And it's now also a great industry for a lot of other experiments. And I also wanted to mention this because the Sunyaev of the Sunyaev-Seldovich effect is sitting here in the audience, Rashid Sunyaev. He comes here to the Institute as a visiting professor for 2 months a year, and it's been great having him, and he's been part of this story of the CMB for a very, very long time. It's a pleasure both for me and for all our members to have him visit us. In fact, this curve of the acoustic, this curve with wiggles that I showed at some point, you can see where this curve is coming from. The original paper was a paper also by Rashid in the 70s, I think. So it's a great pleasure. I just wanted to acknowledge the fact that we're really, really happy that he comes and visits us so often. Okay, so I hope I have convinced you that we have a very good model of the universe. You might think that some of these pieces look weird, but okay, fine. That's how it looks, how it seems to be. Okay, so now we are getting a little bit more cavalier, and so we are doing the following thing. We think we understand the physics so well that we can run the movie backwards and try to figure out, even though we have a picture 380,000 years after the Big Bang, we want now to understand what was happening even earlier. We run the movie backwards, and we think we can tell you exactly what was happening at the very beginning of this hot Big Bang. And in fact, we are even more cavalier, and we say, okay, maybe we can even tell you what came before, okay? And so let me tell you about if you ask somebody, so what came before this hot Big Bang? So you told me this story, the universe was hot, filled with stuff, expanding very fast. What came before, okay? So if you ask this question to a practicing cosmology, he will give you an answer, or she will give you an answer, and I will give you this answer, okay? So the answer is the following. Before the hot Big Bang, the universe was expanding really, really fast. It was probably doubling inside every 10 to the minus 32 seconds, so 0.00032 zeros and a 1 second, doubling inside like crazy, okay? As a result, if there was anything there in the universe, it got completely diluted, and you end up with completely empty space, a humongous universe because it has expanded by so much, okay? And at the end of this process, we call it inflation, and at the end of this inflationary period, the universe starts expanding in the normal way of this hot Big Bang model. First of all, you fill the universe with material to start the hot Big Bang, radiation and everything, and then the story goes on. So we add to the beginning, or to before this hot Big Bang, a very rapid expansion, we call it inflation, and so on. You're probably quite familiar from seeing advertisements of, say, drugs that, like medical drugs, that you see the ad, and there's these beautiful people going around, and there's fields with weed, and everybody's happy, and the sun, and everything so forth. That's very nice. And then at the end of the ad, there will be a voice that goes very quickly and says, look, if you take this, even though you're only for your headache, maybe your head will explode, your arms will come off, a disaster can happen. So fortunately, cosmologists are not forced by the government to put any kind of disclaimers in our statements. And so if you ask us, we will tell you this story and try to move on to go to our office and do our things, okay? But of course, if nothing goes wrong, like in the case of these drugs, everything is good and everything, you're happy, you get cured. But when something goes wrong, all of these little asterisk things that they went through, those are really important. It's kind of the same thing here. Okay, so we think we have a story. There are some reasons why we have this story. I will try to go through some of these reasons. But if something goes wrong, then it may be wrong, completely wrong. The story may have nothing to do with what actually happened. So, but let's try to understand a little bit why people came up with this story. Okay, so this story started around the 1980s. People that are associated with this model of inflation are Alan Guth, Andrei Linde, Alexis Starobinsky, Slava Mukhanov, Paul Steinhardt here now at the physics department. Those are the set of people that are usually associated with inflation. It's very difficult to make this list of people because now that a lot of us think that this might be what actually happens, prizes are being given, and so if you leave somebody out of this list, they get annoyed, they send you emails, so you have to be very careful of who you include in this list. But I'm sure I'm going to get some. Last time I made a list in this auditorium, I got some angry emails, so now among the people I have mentioned are the ones that sent me this. Okay, or the one, anyhow. So what were the problems that they were obsessing about? One of the problems that they were thinking about was these initial conditions of the universe, or questions along the lines, why the universe lasts so long? Why is it so homogeneous? And let me go through the question of why did the universe last so long. I told you that we start this hot Big Bang, and the universe at this time is expanding very, very fast. Every fraction of a second is doubling inside and doubling inside. So you go to your computer and you imagine, say, okay, let me start a simulation of the universe. Let me get going. I use the laws of general relativity, and I let it go. Okay, what will happen? If you're not incredibly, incredibly careful, after a few fractions of a second, the time things are happening, the whole universe will collapse into a black hole, or it will become completely empty. So if you want to make this universe last 10 to the 10 years, even though everything is happening every tiny fraction of a second, it's very difficult. Okay? So they couldn't figure out how to, or they were wondering, it looked like these initial conditions looked what people call very fine-tuned, okay? Very difficult to accommodate. And by adding this period of inflation in the past, what it does is leave after this period initial conditions for the regular evolution that will make the universe last for a long time. So that was one of the original motivations for introducing this period of inflation, the very strange nature of the initial conditions of what looked at the initial conditions for this hot Big Bang. But after that, a lot of things happened. So let me tell you some of those things. So the first thing that happened, think about like a cramped piece of paper that you're stretching like that. What happens? It will become flat. Okay, you stretch the piece of paper, it becomes kind of flat like this. Okay, and the more you stretch it, the flatter it will become. Perhaps it's better to think of something more rubbery than paper. If you stretch paper too much, it probably will break. But there's a very analogous concept about flatness and so on for the geometry of the universe. And inflation does pretty much this kind of thing. Even if you start with a cramped piece of paper, with a thing, the universe whose geometry is not what we call flat, which is very, very analogous to this kind of picture, after you stretch it by so much with this inflation, you end up with a universe which is very flat. The geometry of the universe is very, very flat. And people figured out that by making measurements of the cosmic microwave background, they could tell if the geometry of the universe was like this. And around the year 2000, a telescope called Boomerang that flew on a balloon that took it all the way to the border of the atmosphere, flew it from Antarctica, went around Antarctica for like 2 weeks, make a map of the cosmic microwave background, and discovered that indeed the geometry of the universe was flat, which was a big success for this inflationary paradigm. And I also wanted to mention this because the camera that flew on Boomerang, that made this incredible discovery for us, I was a member here in the year 2000. I remember quite vividly when this was announced, and so it made a tremendous impression on all of us. The camera that flew on this telescope was the prototype of the camera that flew on Planck. So this incredible discovery was made with the prototype camera for what then came Planck bolometers that were built in JPL, the Jet Propulsion Labs near Pasadena in California. So that was a big news and a big plus for this inflationary kind of ideas. And then a bunch of other things happened. So the next thing, and this I'm not telling them in exact chronological order. Okay, even in the 80s, and you have to remember that during the 80s, when the models of inflation were put in place, we barely had any measurements, no measurements of the CMB anisotropies, barely any measurements of this large-scale structure. The field there was no data pretty much. And at the time, the people building this model realized the following thing. So if you think of this period of inflation, it's, the universe is expanding like this. One thing they knew that had to happen is that inflation had to stop. Inflation, then somehow the universe needed to get filled up back with particles. This was called the graceful exit problem at the time, and how to make this happen. And so they managed to make it happen. And by managed to make it happen, I mean using the laws of physics as we understand them. They managed to say that if the universe is filled with a material which obeys the laws of physics as we understand it, then the universe will expand in the way that this theory is saying. After a while, this expansion will stop. The universe will get filled with material, and the hot Big Bang will continue. So they managed to show that you could make a model that satisfies the laws of physics as we know them, that did all of that. Okay, that's not a small thing to accomplish. Okay, even if the universe is not the way the universe started, at least we know that using the laws of physics, you can create something that will lead to the universe. Maybe what happened was something else, but finding that this is indeed even possible was a big accomplishment. And so in a sense, this material that filled the universe at the time had to act like a clock, because the universe was expanding, and at some point it needed to stop this inflationary period to start something new. So this physical system was acting like a clock. So but what they realized, because they were following all the laws of physics as we know them, they were following the laws of quantum mechanics. The laws of quantum mechanics say that there are certain uncertainty principles. There are certain things you cannot do. In particular, this clock that they were building could not tell time perfectly because of one of these uncertainty principles. And as a result, the amount of inflation in different regions could never be perfectly the same, because the clocks in some part of the universe keeping track and telling the universe here to stop inflation will get out of sync with the clock someplace else. Okay, this happened because they were following the laws of physics as we know them. But what they realized was that as a result, the universe will not be perfectly homogeneous. There will be little differences from place to place that could be the seeds of structure for structure formation that eventually we saw in the CMB and led to all of the things that I told you about. So they saw that in their model they could produce these initial fluctuations, okay? So their claim was the fluctuations were produced before the hot Big Bang, in this magical phase that they were inventing. And lo and behold, then came the WMAP satellite, and what it did is by measuring very precisely the anisotropies in the cosmic microwave background, including measuring something called the polarization that allowed them to figure out how things were even moving in the last scattering, these 300, I'm sorry, I'm using terms that I shouldn't be using. 380,000 years after the Big Bang, they could even tell how things were moving, so they showed conclusively that these seeds for the structure were produced not during the regular hot Big Bang, the part with the dark matter and so on, but they were there from before, just as inflation predicted. Again, a huge success. Now, if you run this movie backwards and you ask the question, how was the state of the universe at the very beginning, just after the end of whatever this period of inflation or whatever came before was, one thing that you can see is the following. You can compare these differences, these sizes of fluctuations, as a function of scale, meaning the following. I can compare regions of the universe of a given size. I put this size here, comparing to there, and see how different they are. Then I can take a smaller region and compare them, and I can tell a smaller region and compare them. It turns out that these differences among regions of various sizes, they are all the same regardless of which size you pick to do the comparison. We call this scale invariance. So the differences are the same whether you compare big regions among themselves or smaller regions among themselves, or etc. So this, in fact, one of the things that was very beautiful is that these inflationary models predicted, or when you calculated it, the fluctuations had exactly this property. So this was another big success. But furthermore, people at the time realized that this could not be perfect. The scale invariance could not be perfect. There should be slightly different. The scales that are bigger should be slightly different than the ones that are smaller for very good reasons inside of this inflationary model. And they computed how different they could be. At that time, it was impossible to even measure these fluctuations pretty much on any size. We had some rough guesstimate of how it was at one size only. It was an impossible measurement. Planck just made this measurement, okay? So Planck just showed conclusively that the fluctuations on different scales are not exactly the same amplitude, and the size of the difference when they compare the big pixels of WMAP and the small pixels with Planck are exactly of the size as this inflationary theory predicted, okay? Written down in the 80s. So it was a big success, another big success. So I'm trying to impress you, okay? I will unimpress you later, okay? But I'm trying to give you some. But all of this is true. I'm not making anything up, okay? Planck looked for other things. It tried to see whether or not there are differences in the composition. Is the composition of the universe in one of the regions that they see when they look in that direction different from the composition of the universe that they see in another direction? No difference. And this is another thing that clearly comes out of these models written down in the 80s, okay? And they also checked for something which I worked a lot on, and the person who was in charge of doing this analysis was yesterday having dinner with us at home, and I told him I will mention that this is done, but it's impossible for me to explain what it is. Okay, so they made a very detailed measurement of the statistical properties of the fluctuations, a measurement with an accuracy of 1 part in 10 to the 4, and again, exactly what was predicted came to be true. Okay, so all of this is great and happened. Now, of course, if you I tried to tell you more or less what this theory that was around in the 80s was like, what it had in it, what the predictions of it were. But of course, our theory friends we did not just, at some level myself included, did not just stay in the office and do nothing since 1980, okay? Or move to some other field, go and hunt planets or something like that, no. What they did is started to think more about possible models of inflation and so on. So what happened? As I told you, this mechanism, this inflation, this matter that fills the universe and had this property of keeping track of time and telling the universe when to stop inflating and basically acting like a clock and filling the universe with material. This kind of, you can think of this like, in analogy, it's like a clock. It was a very simple clock, like a sun clock here, very beautiful. It works, it keeps time, you turn it around, everything happens as it needs to do it. There's no moving part. Well, the sun is moving, but there's nothing particularly crazy about it. Now, of course, you can build clocks that are more complicated, and this is what happened since the 80s. All kind of things, crazy clocks of various natures, okay? And so we learned a lot about what possible things could happen during this inflationary period. And what were the things that we learned? First of all, one thing that is good is that this inflationary dynamics is not particularly fragile. You can change the clock substantially, the dynamic, still obey the laws of physics. All of these clocks do obey the laws of physics. They work and they do what they have to do. So it's a very robust framework. But we also learned something else, which was not so nice, and it's the following: that all of these very beautiful agreements between data and experiment that I told you, had a lot of these tests gone the other way, for example, had they found differences in composition, had the satellite found something else, we could have gone through this enormous list of different type of clocks that people have now built and pick out which one would agree with the observations. So it turns out we could pretty much fit any of these observations. We can find a clock that will do whatever our experimentalist friends tell us that they see in the universe. And that's not such a nice state to be at. We don't like to be in a state like this because it looks like we're making no prediction. We're making anything that they can see, we can just, and furthermore, it's not even that we go through this list of clocks and we find the one that fits everything. There's plenty. If we find one, we can produce a lot of them. So that's something that is not so nice, to be honest. And other things that have happened, people have said, okay, maybe inflation is not the answer, something else. Let's put something else in. And I'll talk a little bit about that in a couple of slides. And they've tried, and I would say, although this is probably not an unanimous statement, it's probably a shared by a lot of people statement, but not unanimous. This has not panned out. There's nothing nothing that people have come up with works particularly well or at all. So we are stuck with inflation. We have all of these possibilities, and it's not such a nice. In that respect, the agreement is beautiful. The experiments are awesome, but there's still this nagging feeling that there's something that maybe is not as nice. And then the final thing about these models written down in the 80s is that they predicted something else. They predicted what we call a stochastic background of gravitational waves. So what is that? So just as light is the waves associated with the force of electricity and magnetism, associated with the force of gravity, there are other waves which we call gravitational waves, and we have indirectly seen as produced by orbiting objects in our universe. But the claim from these models in the 80s was that in addition to these differences, these seeds for structure formation, a lot of gravitational waves should have been produced during inflation, okay? And furthermore, when you do the calculation, you realize that these gravitational waves should show up in observation of the cosmic microwave background anisotropies that I've discussed with you, and in another measurement of the cosmic microwave background related to its polarization, which is another property of the cosmic microwave background. They should show up, signatures of them should show up there. And we have not yet measured the polarization. Planck has done some measurements but has not released the results. And that's the best channel to look for these gravitational waves. So what I'm going to say is not conclusive, okay? But they could have shown up already at the level of the maps of the temperature of the microwave background that Planck has already produced, and they have not shown up, okay? And the same statement from the maps that WMAP produced. So this is also something that is not as nice, okay? We have not looked as well as we can look, and we're going to look as much better than we have looked so far, but they could have already shown up, okay? That's kind of the statement. This signature could have already shown up and has not. So what should we do? So let me in the last part of my talk, let me just talk a little bit. What should we do about inflation? Should we take all this evidence seriously? And this is a debate that maybe rages more in the popular literature than it does in the scientific literature. For the most part, most people are complete converts, including myself, probably. If I had to pick a camp, I'd probably say. But so let's try to understand what's going on. So I will do this by an analogy, okay? So let's think of the universe as a chicken. Okay, the universe is a chicken, and what we have done is we have beautiful pictures of this chicken as it grows up. So we have pictures of a little chicken, bigger chicken, and we can now understand the chicken was like this. This means it will grow to be like that. We find a picture, everything good. The chicken that walks in this direction will have very beautiful pictures. Now, of course, the first question everybody asks is, where does the chicken come from? And our theory friends in the 80s came up with an idea. The chicken comes from an egg, okay? Of course, you have to imagine that we have not seen any egg. So we don't have a picture of the egg. We have a concept of an egg, okay? So we think, and the egg is kind of inflation, okay? So the chicken might come from an egg, and so our experimentalist friends work hard, and they can pictures from the earlier chicken, trying to see some evidence for the egg, and eventually they come up with this picture. It's not really like this. If it was like this, probably everybody would be sold. But so it's clearly a very young chicken. We have a picture from a very young chicken. There looks something on the back. It looks like an egg. Okay, but we don't know what an egg looks like. So maybe all of this, the nest, is the actual egg. We don't really know. And when we do the calculations, and probably the image is much blurrier than this, and maybe this is an egg, maybe it's not an egg. So this is kind of the situation that we are at. So what is the obvious thing to do? I think the obvious thing to do is to try to get better pictures, to see if we can get a picture of from some other angle, see if there's something about some property of the egg that we can compute, and then we can match to this that we are now saying might be the egg, or maybe this is the egg. This is how we can make progress, and this is what we are trying to do. Another thing that we can do is go back to the office and just think. Not try to get any more pictures and think. And this is what happens when you think. Of course, when you think, you run immediately into the chicken and egg problem, okay, with which I amuse my daughters this day, okay? So, but we cosmologists, we are stuck with this chicken and egg problem. So if we say the chicken came from the egg, where does the egg come from? It comes from a chicken, et cetera, et cetera. You know the chicken and egg. Okay, so, and if you look at this, if you look at a paper or a magazine article about these debates on inflation, you should think in the back of your mind really about this chicken and egg problem and try to see if the arguments about inflation are whether or not the actual, is it something, are they making an argument about the picture itself? Are they saying that what we think is an egg is not really an egg because eggs should look different than this? Or are they basically talking about the chicken and egg problem that we don't know how, you know? And most of these arguments, if you replace universe by chicken and inflation by egg, you will translate the whole thing. And most of the arguments are a dressed up modification of the chicken and egg problem. And so, okay, we can debate the chicken and egg problem for a long time, and that's fine. But it's not obvious that we are going to make a lot of progress discussing that. Then there's another you know, group of our friends which are already sold. Okay, of course, the universe comes from, or the chicken comes from the egg. And of course, if the chicken comes from the egg, there's a lot of chickens. Clearly, there's a lot of chickens. There are eggs all over the place. All of these chickens, remember, this chicken is a universe. Each egg is something that creates a universe, okay? So there's chickens all over the place. There's eggs all over the place. And what we need to do now is compute the distribution of the sizes of the chickens, how many big chickens there should be, small chickens, and so that's another, and this has a technical term, it's called the multiverse. People do talk about this. They think that there might be many more universes, whatever that means, inside some bigger structure that is the multiverse. And each of these universes sometimes even creates a new one, gets an egg, there's a new, you can again do this translation and you will get a lot of mileage out of it. And in fact, you know, chickens are walking, they can even collide with each other, the chickens. And in fact, two of these universes can collide, and these are bubble collisions, we call them, and there could be signatures of these chicken collisions. In the chicken, something happens to it. And we look, in fact, we try to see, maybe this is true, the whole story is true, and there is our chicken has collided with some other one, and there's something in the sky. We indeed look. It could be. I'm not saying it cannot be, but okay, so clearly we don't want, it's fun to think about all of these things, but we don't want to descend completely into some, you know, swamp in which all we debate is the chicken and egg problem and try to calculate properties of imaginary chickens that we have not yet figured out. So probably most of the progress will come from doing what? From just getting more data, getting more observations. So let me tell you a little bit about what we are hoping for in the next few years in terms of new results, new observations. And all of these results and observations will come from ever better telescopes, bigger cameras that allows us to look further back. So one thing that, well, maybe the zeroth order I should say is that the first thing that will have to happen is to clean up some of this mess that Planck has produced. And what do I mean by this? The experiment was great, but now some things that we thought we knew from other experiments are not quite working out. And this usually happens when you get a much better data. Some of the older data is not particularly perfectly consistent, so something might be wrong. And you know, we are all humans, and so scientists, I mean. You know, the best thing that you can do is get a discovery, a measurement, something that you find. The next best thing is to find that somebody else's discovery was wrong, okay? So as a result, now that there are these little inconsistencies, and believe me, they are really little at this point, but we are going around, who screwed up? Were your error bars too small? Were these one of the unknown unknowns of Donald Rumsfeld inside of your measurement? Who made a mistake? Is it Planck that made a mistake? Is it WMAP that made a mistake? Who's made a mistake? So this is going to happen in the next 6 months or a year. We're trying to settle down all these little discrepancies. But more importantly and more interestingly, Planck has crossed this barrier in which they can make these detailed measurements that involve combining many pixels and many in the maps to measure, for example, this map of the dark matter that I showed you. And this is now being done by many other experiments. A lot of people are trying to do this. So we've crossed a barrier in which we can map the dark matter through this gravitational lensing. And so we're running to try to make maps of the dark matter the best we possibly can. The other big barrier that we want to cross is this polarization measurement. I didn't say much what the polarization was, but it has inside this clue of the gravitational waves that may be from inflation. And so Planck did measure polarization. It did not yet release the results. Next year they will release the results. We don't know if they'll have the sensitivity to go after these gravitational waves, but other experiments are trying to do that. So that's another race that is going on. Furthermore, we have this very detailed model that makes these very nice predictions. We are trying to see if we can make it break anywhere, okay? Is there something wrong with it? And especially on the smaller scales, sizes, structures, smaller structures that form later in the universe. Is there something wrong with it? And in fact, for example, we do believe there's some place where it might break fairly soon. I didn't say very much about this, but the universe is filled with neutrinos. We know these neutrinos have a mass. And as a result, they affect the process of structure formation. We have never been able to determine the size of this mass in the laboratory, but we think that these measurements are so good that they will allow us to see the effect of this mass of the neutrino in the cosmic structures. And so we're trying to make these gravitational lensing effects measurements better and better to try to pull this out. That's another thing that we want to do. And finally, if I take a step back as well, when I said about the composition of the universe, that 5% is made of regular matter, 27% for dark matter, the rest for the dark energy, we've been miserably bad at calculating from first principles any of these numbers. If we wanted to calculate how much regular matter we expect, we call this baryogenesis. At this point in time, we don't know how to do it, or it doesn't come out right. The amount of dark matter, we don't know what it is, and so we cannot calculate it very well or at all. And the dark energy is just a total embarrassment that I will not even go into because we get numbers that are just too ridiculous. Okay, so that also, of course, we would like to make some progress, some theoretical progress, or maybe some measurements on the accelerator in Switzerland will allow us to make some progress on that. So clearly, we want to make some progress on that. So I would say, I hope I have convinced you that we have built a very beautiful model of the universe through observations. We have seen how the universe evolved through cosmic history. We have a lot of data. We have very nice models that agree with the data and the observations. We clearly understand a lot. We want to understand many more things. To understand those new things, we have to get very creative and be able to build better experiments, better telescopes, better cameras, and be able to calculate better than we can today the predictions from these models, to be able to compare them with the observations as we go along. So we need to do that, and of course we rely on for this we need of course the help of the whole society, that through their tax dollars, philanthropic contributions, etc., are the ones that fund all of this research that we do, and for this we are of course very, very grateful. And I'll stop there.